Okay, so welcome to this, let's see, 11th lecture of this course. So we have only 4 lectures left actually, and it's only 3 of those lectures we do, new antennas, and in the final lecture I will do one, example exam as repetition for the course. I have also uploaded a few old exams on the Canvas that you can take a look at, because we're getting closer to the the final exam in January and the end of this course. So yeah, also this week, you know that the last part of the lab is coming, and in that lab, there you're really going to build your second antenna, or even actually third antenna, because you have done 2 patch antennas. And that means you have to build your own reflector antenna and bring with you to that lab. That happens so pretty quick. But it's also an antenna that is, I shouldn't say it's simpler to actually manufacture and design. Of course, to build a big reflector antenna is harder, but you don't do it in the same way where we first simulate it and we check everything in detail. We do a very robust, or you should do very robust design. And that means today we're going to look at those antennas. And that is a reflector antenna that you're going to build and bring with you to the lab, which is a larger antenna with higher directivity, so more narrow beam width. So that is what we will do today. Before I start, I should also ask you if there is any practical things, something you wonder about the course now when it goes to its end before we start. Okay, if there are no questions, then give questions whenever you have during the class, and that means that we start. So what we will do today is to look at this radiation from apertures. And that is then something that's done in a particular type of antennas. So we will look at here, for example, horn antennas, so these type of antennas. And what you call an aperture is that this is an aperture. It's basically radiating from the stuff that sits inside of it. It also comes to reflector antennas, which we treat in a similar way. And in the end, we will look a little bit at lens antennas, which is getting, I would say, more popular also nowadays, because we go up in frequencies. So we start talking about 60 gigahertz, 100 gigahertz and above. And there we start with structures that get more similar to optics. And you know, in optics, you typically build lenses to have a magnification of your system, for example, a microscope and so on. And the same thing happens with antennas. So aperture, horn, slot, and reflector antennas. So this is an example of a broadband horn antenna. So you can see it has some shape, it has something inside here, and a little bit of ribs that sit there, not so much. That's a horn antenna. This might be a more typical horn antenna if you've seen it before. And in this picture, you can really see this aperture part. So when we look at this, you see the top part that sits here. That is then the aperture. So what it means is that the radiation is in some ways created down here, something happening inside of this. But when we look at the radiation, we just take the pieces that sits here and we say everything passes through this aperture. So when we want to know the radiation, okay, how big is the aperture? What is the field distribution in the aperture? That determines the radiation pattern in some ways. That gets a very simple and very powerful view of these type of antennas. And of course, when you look at this one, you can see here are some holes. But even if those holes are there, the real aperture, when we think about it, is still this piece here. And it just can, it can simplify the manufacturing, reduce materials, so some ways remove pieces that doesn't really matter. And almost all the radiation in these antennas still passing through this aperture that sits here. So it's also an aperture antenna. Another type of aperture antennas are slot antennas. And here you can see a slot array. And all the slots are the small holes that sits here. So it's an array because you can see that there are many slots, and then the radiation has to pass these small apertures in some ways and radiate through the apertures. And that also means it can be a practical antenna, because in many cases you have some hull or something, for example, an airplane, a boat, or car, and you can make some small holes in that mechanical structure, and there you can actually fit your antenna, and it means it doesn't need to, in some ways, take away the mechanical properties of that structure, because it can be okay to make small holes, but not large holes mechanically in some ways. And the slot array is a good example of that. Another example, which is the antenna you will build, is this reflector antenna. Or you don't have to do exactly this one, but it's a type of reflector antenna. This is a parabolic dish. You have all seen it on typical rooftops, balconies, and so on for satellite TV. It's also used a lot in base station for point-to-point communication between base stations. Small dishes sitting there. And in this case, the radiation actually comes from the feed that in this case sits there, and it radiates to this one, and then it radiates out from it. So it's not exactly the same as this horn antenna type or slot antenna when it sits from underneath, but it's still passing through the aperture that is covered by this dish. So we can say that even if the radiation is created outside of it, it actually comes from that aperture. So we typically analyze reflector antennas as a first case, actually as aperture type of antennas. So the first thing we have to do today is to look at radiation from these apertures to understand how does these antennas radiate. So to do that, we do what we always have done in this course and what you do for antennas. You start saying what is causing the radiation. And if you think back at your first favorite antenna, your dipole, and of course your patch afterwards, when we determine the radiation pattern from this, we said that the radiation comes from the current that we induce on the structure here. So in this case, we have a real electrical current flowing, we have charges that are accelerated, and that acceleration causes this electromagnetic field to radiate. When you looked at your patch antenna, instead we said that we had some equivalent currents here and equivalent currents here, and it looked like the radiation is coming mainly from one magnetic dipole there and magnetic dipole there. And that when our magnetic dipole, we have to basically turn the polarization or say that the magnetic field is dominantly parallel to this magnetic dipole. And we do the same thing with apertures. And with apertures, we just add that both the electric current and magnetic currents exist at the same time. And in this case, we have what's called equivalent currents. So similar to what you had in the patch. Because in the aperture, there is no metal. There is no charges flowing forward and back. But there is an electric field, there is a magnetic field. And from the case here with the magnetic field, we can create then equivalent electric surface current. And that will be actually current that then lives here in this aperture. So it doesn't live on the metal, it actually lives in the air in the aperture. And it's an equivalent description that helps us to understand what is happening. In reality, of course, it's only an electric and magnetic field there. But we construct this and they give the same radiated field as this field radiating of this electromagnetic field. And if you had the electric one, then we do the same as we had in the patch antenna. We do add a magnetic counterpart. And the magnetic counterpart comes from the electric field instead. So maybe you see first and think, did I write this wrong? Why do I have an electric current that comes from the magnetic field and I have a magnetic current comes from the electric field? But that's the way it is. You can think about those first case in units. So if you take the electric currents, here in case some ampere per meter, because it's a surface electric current, yeah, it's the same unit as the magnetic field. So actually they do relate in this way, that it's electric current that belongs to the magnetic field. Magnetic current belongs to the electric field. And think about the units for them, and you get that correct. So that means that what we do is that we say that we have some aperture. So in this case, I can just simplify here my, what is a horn antenna to this case here. So I only focus on this aperture. And in this aperture, I have some electric and magnetic field. That electric and magnetic field will create this current. And what is happening in the formula of this is that I also have this n hat, which is the normal component. So n is then a vector that goes straight out here. So that means that if I have a magnetic field like this, the cross product turns it 90 degrees. That is what's happening when you multiply with that one. And that creates this equivalent current. And then comes the beauty, because now when we've done this, we can just do what we've done all the time in this course. As soon as you have the currents, you can take these radiation vectors, which basically is the Fourier transform of your current density, and that will give you a radiation vector. In this case, we have electric currents and magnetic currents, so I will get an electric radiation vector and I will get a magnetic radiation vector. So the magnetic ones comes from the magnetic current and the electric one from the electric currents. And exactly the same as before, you just take these ones, you multiply with this phase factor. And now, since these were surface currents, you only have to integrate in this case over the surface. So these are not volumetric currents, these are surface currents in this case. I don't distinguish those in notation in this case. So these are only living on that surface. You integrate over that surface, you get the radiated field, and you have to, of course, remove the the radial component, because your electric and magnetic fields are perpendicular to the radial component. And then you have your radiated electric field. So that is how we determine the electromagnetic fields, the radiated far fields from the electromagnetic fields in the aperture. That is how we do this procedure in some ways. And that means that everything we have learned can now be applied. So it's the same thing as we had before, you know. We did it for this one, we did it for the patch, now we do it for the aperture. The same procedure. The big difference in these cases is that typically this structure here, it doesn't have to be it, that one is typically larger than lambda, or even larger than many lambda. It doesn't have to be, it's not in slot arrays, but in these kind of horn antennas, parabolic dishes in some ways, they start to be large. They start to be electrically large. And that means that the patterns is typically changing a little bit. But the procedure is exactly the same as what we've done before. So let's now say that for simplicity, we take the typical cases. So again, like this. And in most cases here, this aperture here is flat. We can, of course, have a bent aperture. We can have some strange shape on it. But, you know, let's leave the technical details to the next course. Let's do the ones that we can get the understanding. So we should get the physical understanding. We should understand what's happening. So let's take the simple typical case that the aperture is planar. It's the most common case that we have. So that is the one that we will really focus on. And now we say that this aperture here, A, is in the XY plane. So it's basically flat, and the Z component is then normal to it. That is how we put the coordinate system. And that means that we need to integrate here over dx and dy, because we have to integrate over the surface in these cases. And then we can rewrite our integral here. So this way and this way for the electric radiation vector and magnetic radiation vector. I had the phase vector here before, and I had before written it in this general form as J, K, R scalar product at R hat. And now we can simplify that, because we can actually put in what this R hat is in this coordinate system, so what is X hat and Y hat and so on. And then we just get the multiplication here with some wave numbers Kx and Ky. That then depends on the angle that comes out and the wave number K that sits there. And now if you look at these ones, do you see the Fourier transform? Say yes. Yes, you see the Fourier transform. This is a Fourier transform. So you really Fourier transform from your, physical coordinates that sits here. You have X, you have Y, to radiation. So in the next case, you're talking about the angles that goes out, the radiation over the sphere in some ways. And the relationship between those is this Fourier transform. That is what comes up. In this case, it's of course that they are limited because you're only interested in certain angles here, theta and phi and so on. But there's really the Fourier transform relationship between them. It's very clear from the way that this formula is written in this case. You can really see it is a two-dimensional Fourier transform of the current density in the aperture you should have. And then you start thinking, do I know a lot about Fourier transform? All of you raise your hand and say, yes, you do, because you have studied Fourier transforms in many courses. You've seen what the Fourier transform looks like. And you typically have looked at pulses that you should know, for example, this rectangular pulse. You have learned that the Fourier transform of the rectangular pulse, you've done it in the time domain in most cases, is the sinc function. Do you agree with me? I hope you do, because you have learned that. And how does this sinc function look like? Yeah, that looks like this. And then start thinking, what does a typical radiation pattern look like? Yes, you have a main beam in this case here, and you have some side lobes that sits there. Okay, what would that mean? It would mean here, for example, that these electric fields, let's say they're equal to some constant in this aperture. That means that when you're outside of the aperture here, you are there. There is no electric field outside of this aperture. Inside of the aperture here, you're sitting there. You have some amplitude of these electric and magnetic fields. So at the edge, you just go from 0 electric field to high electric field, which translates, of course, to that the current here going from 0 to something. You have this little jump. That is a jump we see here. And then it's fairly constant in the aperture in the first approximation. And then it goes down, and then it's 0 again. Of course, radiation vector is then this sinc function. So that means we can actually know a lot about this without doing anything. And this is a very typical pattern you get out from this type of apertures. You get a main lobe in the forward direction, and you get some side lobes that comes there. And it actually tells you afterwards how should you put down the side lobe levels. And the way you should do it is to make sure that you have a tapering here over the field when you go to the edges. It should go smoothly down. That will push down your side lobe levels. And in many cases for our apertures, that's called tapering of the illumination of this aperture. So Fourier transform the equivalent currents to calculate the radiation vectors. That is the basic principles. The details of the formula you have in the formula sheet. That's fine. We might forget what, for example, these angles are, you know, the details of it. But that you take the Fourier transform of it, you should for always remember. That's not something you need a formula sheet for. That is really sitting in your understanding of this type of radiation and these type of antennas. So let's do then the calculation, exactly the same calculation as I mentioned on the previous slide. So we take an example where we say that we have an electric field in the aperture. So I take a rectangular aperture. I say that the electric field is now in the y direction. So the electric field is pointing up here. If I now put this as x, I put this as y. And I say that the magnetic field in this case is equal to 0. Just do that for simplicity to see what's happening. And if I take the integrals that I had in the previous case, I actually have this Fourier transform of this 0, 1, 0. And that is the sinc function that gets out there. So I can use this integral. If you don't remember Fourier transform, you can just do it by paper and pen in less than like a minute in some ways. You just integrate this exponential function. You get the sinc function. And plugging that in, yeah, you get your magnetic radiation vector here. And when you look at these ones, you see here, one sinc function and one sinc function. Because you integrate this over x, you integrate it over y, but they decouple. So you can do those separately. You can first integrate over x, and then you can integrate over y. And now you have your sinc function. And we plotted in here what all of these angles are in this case. That means that we can remove those, the radial component, because we should eventually take these ones away. And that is due to that the magnetic current here is now in the x direction, because the electric field. The magnetic current is in X direction because the electric field is the Y direction. Even I'm mixing up this one sometimes. And the typical plot now of the sinc function is here. So this is a typical plot of what this radiation will look like from an aperture that you illuminate. So here you have a main lobe, and here you have a first side lobe, second side lobe, and that means you have some side lobe level where they go down a certain amount in some way, some dB down in some ways. And it's coming then side lobes further and further out. So this is your sinc function that is plotted, and that is the typical radiation pattern that we actually have from these type of antennas. So if we plug in some more, realistic case and start looking at how this pattern behave as a function of the size of the aperture in wavelengths. So if we take this in, we plot in whatever it sits here. You can see you can take the formula sheet. You get a Hughes factor here. It doesn't change the shape of it. And here you get one part, which is that we removed the radial component in the radiation. The electric and magnetic fields are always perpendicular to r hat, so you have to take that away. And then we can start looking at what is the pattern for different number of wavelengths. So if I start here with 5 wavelengths, you can see here that you have, again, a main beam in the 0 degrees, it's radiating straight up. And that's of course because you have a constant field, constant phase over the aperture. So think about an array is radiation in the broadside direction. You can see some side lobe levels that comes here, and you see a certain number of side lobes and dropping off when you go down. If you change these ones now to 10 lambda sitting there, you can see again main lobe. You can see more side lobes that comes here. You can also see that the width here gets more and more narrow. So the larger you make the aperture in wavelengths, the more narrow is your beam, typically higher directivity. Exactly the same thing, that's what happened with arrays. Typically, if you look at a uniform array, you can see you started with 2 elements, 3 elements, 4 elements, the beam got more narrow. And an equivalent way of looking at that is that the total aperture is increasing in number of wavelengths. Because if you had an array with half a wavelength, 2 elements is half a wavelength, 3 elements is 1 wavelength, 1.5. So the aperture gets larger and larger the more array elements you add. The same feature happens here. And if we plot it now for many of these sizes, so you can see here it starts with 1. So the blue curve that sits here, in this case, this one, that means that here Ly is equal to lambda. So your total aperture in this case, the aperture where you had your radiation, that size here was then 1 lambda. And then when you make the aperture larger and larger, so you go, for example, for the red curve that sits here, then Ly is 2 lambda. And you can see then it's starting to form a main lobe, it starts the first side lobes, and that means, of course, in the red one, this one was 2 lambda in size. My 2 is not so easy to read, so that is 2 lambda. And then with the other colors, it goes higher, so 3, 4, 5, 6, and so on. And in the black one, in the end, it's 15 lambda. And you can see all of them, the beam gets more narrow and more side lobes comes in. That is the typical thing that's happened with an aperture and all of this type of aperture type of antennas in some ways. So one thing we could see now was that you had an effect that you got side lobes. And that you had in arrays. So a week ago, we approximately had this, but we had this, fixing of the array pattern. So we try to change the pattern to reduce the side lobe levels. We see the same thing with arrays. And the conclusion that we could draw was that in these cases, the side lobe levels comes in some ways from the discontinuity of the field close to these edges. So if you had this homogeneous field, so constant field in aperture, go down to 0, and then outside it's of course 0. You got this Fourier transform of the sinc function, you got a lot of these oscillations. So then we should of course push this down in the same way as we did with this Dolch-Chebyshev and binomial distributions, what did we do? We tapered down this illumination of the edge elements. So we put less power or less amplitude on the elements on the edges. And that, of course, we can do with an aperture. So instead of having here a field that looks like this, that creates then this pattern, because you take the Fourier transform of your aperture distribution. So let's do something smoother, for example, something that goes like this. That looks a little bit like this binomial array, like smoothly tapered. Yeah, then you can get a radiation pattern here that looks like the same. So you can take away these side lobes by in some ways tapering the amplitude of the field closest to the edges. So it gets more smooth. And then you would push down the side lobe levels. So if you look at some examples of this, we can see it illustrated, for example, here, that in the first case, what's happening formally here is that if you have a discontinuous function, so in this case, you have this, as a discontinuity, it means that the Fourier transform decays very slowly. So when you take the Fourier transform, you actually have a decay that's only 1 over the Fourier transform parameter. And if you smooth it, so also for example, the function is continuous, but the derivative is discontinuous, it goes 1 over xi2 and so on. So increase the smoothness here to increase the decay. And yeah, large discontinuities create high side lobe levels. It's a general thing that sits there. And if we look at then the FFT, or the Fourier transform in these cases, maybe not the fast one, it doesn't matter. We can see the example here. Here you can see this rectangular shape as you had for array antennas, and now we have it here. If you take the same distribution and you smooth it, here you can see the side lobe levels then go down. And that's the same thing as happening in the Dolch-Chebyshev binomial array and so on. You take them away by making it smoother and smoother. So in this case, it was a little bit smooth because it's a cosine x. If you do a cosine squared, it's a little bit smoother, and you see it's down even more. And that's good. But of course, when you do that, you also use less power on the edges here, so you don't utilize your full aperture. And then you can say, let's compensate between those, so have almost maximum aperture in the center, and then a little bit smoother down, and then you are somewhere between these two levels. So this is the way you can play with your aperture and illumination, because you want to use it as efficient as possible. You want to use as much as possible, but you also want to taper it on the edge, because then you push down the side lobe levels. And you want the side lobe levels to be as low as possible, but you also want your beam width here to be as narrow as possible. Same thing as with an array. And these are things that you typically play with when you try to design your illumination of the aperture to get a good radiation pattern. So now we have some ideas, of course, what we would like to do with an aperture. We just look at that as an abstract setting. Now let's look at some antennas. So if we take the first and most simple aperture, then we just take what's called an open-ended waveguide. So what this means is that I have an aperture here. So here is my aperture. So here is where the radiation is coming from. It's coming from this aperture here. So somehow I feed the structure in here. So here I put a small antenna, like a monopole or something just sticking up the inner part of a coaxial cable. That is what's seen there. And that, of course, generates inside here a lot of electric and magnetic fields. And now they are in a very, good environment, because you have this rectangular shape, as you typically have in horn antenna here, this bottom part here, that is this waveguide section. There we know everything that happens, because here we can actually solve Maxwell's equations, and we'll see it very soon. And then those fields will in some ways move out here from where I generated to the aperture. And then I have a good idea what the electric field is in this aperture. And then this aperture will create a radiated electric and magnetic fields that comes out. And that is my radiated field. And I do that by taking the Fourier transform of the field inside of this aperture, of the equivalent currents inside of this aperture. And that is now called an open-ended waveguide. And a typical case with this is that this structure here, if you would guess what is the size of this structure typically, it's typically lambda over 2. That's where you sit. Maybe it's slightly larger than lambda over 2. So between lambda over 2 and lambda in some ways. Again, it comes into these things that is where you have good determined solution to Maxwell's equation. This is what we call the lowest order mode in these cases. So you get something to radiate when this is of that order, lambda over 2 to lambda in some ways. And that means that this aperture here is of course quite small. And if the aperture is quite small, you could see it on the previous picture. What does that mean? If we go back here to remind us what that meant, that is typically what you have down here, this blue one. Then the aperture was of the size lambda. So if this is even lower, it means that the radiation pattern here really is wide. It's a very wide beam. And again, think your Fourier transform. If something is very narrow, you Fourier transform it, it becomes very wide. So small aperture, wide radiation pattern. If you want a narrow radiation pattern, you need a large aperture. That's why I need to go between these ones. So if we go back here, it means that I would like to make this aperture larger. Because if I make it larger, I can push the radiation in the forward direction. So how do I do that? I add a horn to it. So I take the same structure as I had before. Here I have my open waveguide. So this is now exactly the same structure. And then I add outside of it something that now makes this structure larger. So if this structure here, say, is around lambda over 2, it means that this one is then larger than lambda, if I just make it wider. And again, that's what you see here. Small structure, size lambda over 2 to lambda, larger structure, a few lambda. So I can make it grow out in some ways. And still I can preserve a good field distribution here that make this radiate. And that is what you do with the horn antenna. That's basically what's happening with the horn antenna. So we widen this cross section and then we increase the directivity and gain of it. And of course, you can also see it from the formula that we had, I think, on the first lecture. We looked at the effective area of the antenna and relate it with the gain. And again, here, what you can see is that the area here is normalized to the wavelength. And the larger that effective area is compared to the wavelength, the higher the gain. So you want this area here to be many wavelengths in size to get a large gain out. That's what you want to do. And if you think about this as a receiving antenna, take the opposite property here, then it comes in electromagnetic radiation here. You can think about small particles. And here, you know, the particle come here, it bounces in. If it comes here, it goes on the side. And that's not exactly what's happening with this because it's too simplified. But a little bit as a picture, of course, a larger aperture would capture more of this incoming radiation. And in transmission, it makes the aperture larger, which increases the directivity out and the gain out. So the horn, it acts as this gradual transition from the waveguide mode to a free space mode. So you have some smooth transition here that just makes it larger. That is what you do with the horn antenna. If you look at typical radiation from it, so this is Infeco, you have the simulation files on Canvas, so you can simulate it yourself. You can see a typical radiation pattern here. So in this case, you come up to 20 dB gain, so pretty good gain of this structure. You can see here that you have some side lobes that comes here. You have lower side lobe in this direction, and typically a horn antenna has one type of side lobe in one cut and another one in the other cut. It depends on the polarization. Here you can see a field that looks very simple and nice. And that is a mode, the electromagnetic mode that can live inside of the waveguide. It have a very well-determined property. We can write it down by a simple formula, what the electric and magnetic field looks like inside of this waveguide. And then here, it's the current that we see, so we don't see the field, we see the induced current. You can see it's strong currents here, and here the current is basically equal to 0. And that has to do with the direction of the electric and magnetic fields. So it's the polarization that comes in. That makes those different. And if we make another view of the same thing, and we actually look at the electric and magnetic fields in this horn, you can see the same thing here, because now you see the radiation here again in the waveguide. Here you can see it starts coming out, and basically here it bends around the corner. It's also radiated downwards. In this case, it's almost zero, so it leaks over less to that side. And you can also see that the field is stronger on this edge than it is on this edge. And that means that the tapering inside of this aperture is actually different. It's not constant. It's constant in one side, but not along the other direction. It's like a cosine shape in one, and it's a constant in the other one. And I can explain it from the left figure. So in the left figure, you instead see the cuts, which are horizontal. So when you are far down here, I can see if I can stop this. So when you're far down here, you see that it's a field inside of here, very low field outside. And when you start moving up in these cases, so what you can see here is that the field is very strong here, but it's weaker on the edge there. It's basically zero on the edge there. And if you would draw a picture of this, it will be, if I have the aperture here, I have a field that looks like some cosine sine shape here. So it's equal to zero there, but it's equal to, yeah, let's say 1 on this side here. So it's only goes to zero on one side. And it has to do with that the tangential component of the electric field here has to be zero. So if the electric field now points in this direction here, it is zero on that wall, but here the amplitude have to go down to zero, because here it only has a normal component in that direction. So that is the solution to this problem inside of this structure, and we will write it up very soon with formulas, but this is an illustration of the same thing. So to understand this, we then have to start with this open-ended waveguides, because we saw that the radiation starts inside of the waveguide. And then we can see, is that actually used as an antenna? And in many cases, it's actually called a probe. And an open-ended waveguide, that we, for example, see here, it is the standard equipment to, for example, measure electric and magnetic fields close to radiating source. And that is called a probe, open-ended probe. So it's not perfectly matched or something, but it's rather small. It doesn't stick out, and it has really no side lobes because the aperture is so small in these cases. Here you can see a typical aperture of this. So this is the aperture you see there, the same part of the structure. And this is a model that would see in a radiating case, what does the electric field look like? So in this case, the electric field is pointing in this direction. And that means that the tangential component here, so you have that n hat cross E has to be equal to 0 on the walls. It's always satisfied because it's the normal direction to the electric field. So sometimes you have this, that ET is equal to 0. So the tangential component of the electric field is 0. If you look at this direction here, then the electric field is parallel to the wall. And that means it would have a tangential component, but that means the amplitude of that one has to be 0. So in total here, you have an electric field here, which is 0 on this wall. It has its maximum there, and then it goes down to 0 again, and then a polarization in this case. That is the lowest order mode that can exist in a waveguide. We'll write up the solution to it soon. And yeah, vanishing tangential component of the electric field, that is what gives this solution. And then it's like a Fourier expansion of that field to give modes. Expand it in modes, exactly what I say, and only the lowest order propagating mode, and that has a cosine shape. And the structure that we see here is actually used as probes to measure electric magnetic fields. So this is a measurement probe that we see in this case. This one here is for 60 gigahertz, this probe. So it's very small. The aperture is very small. And to really measure the field, we do something that's called probe compensation, because this doesn't really measure the field, it just measures the signal. So we have to compensate in these cases. If it comes in here, some electric magnetic field, we get out some signal that sits down here. And that, to compensate for that, is called probe compensation. And it's done in all measurement systems. So I mentioned this solution to this. And what can be seen in these cases is that the wavelengths to get a propagating wave in these cases comes from the solution to Maxwell's equation inside of this structure. So to be able to get this solution, which is the lowest order mode, the angular frequency has to be over the cutoff frequency for the lowest order mode. And if we reinterpret that in wavelengths, to make it simpler, we say it's in free space, it means that the wavelengths here has to be below 2 times the maximum dimension of the structure. And again, that is that it has to be at least half a wavelength or shorter. So if the wavelength was longer than half a wavelength, actually it doesn't exist any propagating field inside of this waveguide. So that means that we, in some ways, by looking at the size of the waveguide, we can say what kind of wavelengths can exist inside of it. And horn antennas and all of these antennas are designed to have the lowest order mode. And that means that we basically know what the cutoff is for the lowest order mode by just looking at the maximum dimension that sits there. And in this case, it would be the A, because A is larger than B. And that means that when it's half a wavelength for that dimension, it can start propagating. And then that can be used to approximately 2 times that one. Or we have to look at when it comes in the other direction of B. So frequency is limited by a cutoff frequency in the waveguide. You can see part of the derivation is in the lecture notes in the appendix. And the cutoff here is that we need to fit half a wavelength in the cross section for a propagating wave. And we don't want more than one propagating wave, because then we don't really know which mode is excited. So they're designed to only have one propagating wave. And that is deciding what are the bandwidth of this structure. In what frequency range can we actually use this antenna? That comes from those dimensions. So if we consider in the simplest case here, a rectangular field waveguide again, and now we say that A is 2B. So it's the double width to the height here. It's a fairly typical dimension that sits there. We can again get out the cutoff frequencies here, so we can solve them. And in these cases, you can see these modes here, M and N. Think about those as the Fourier expansion. So the higher modes, the more and more oscillations. So you will get a higher mode here that basically could look something like this. There will be a higher mode. So that will have M equal to maybe 3 or something. You want to sit at the lowest one. So M or N equal to 0 or 1. That's what you would like to have. So you have the cutoff frequencies, the lowest one, speed of light divided by 2A. And then you can have the higher one, which is the double to that one. And in these cases, you have a frequency range from the lowest mode to the second mode. That's where you can use them. And the center frequency between those ones would then be 3/4 of this dimension. That is the center frequency. So lowest at half a wavelength, and then basically go up to 1 wavelength of these ones. And the fractional bandwidth, if you just look at what to say from the lowest mode to the second mode, if you calculate in these cases, it's approximately 66%. So that is approximately what you can get out from horn antenna. But then in reality, what's happening is that you never operate those very close to cutoff. You need a slightly safety margin. So in reality, it's typically around 40%. So you have some center frequency and you have a bandwidth of frequencies around that where you actually can use it. And it comes from these mode expansions in the waveguide that sits underneath this type of horn antenna. So if we now do this open-ended waveguide, we just do this one before we take a break, then I can take these mode solutions in the waveguide and I can actually write them up. So these are the electromagnetic fields that exist in the lowest mode propagating inside of this aperture. And what you can see again here is that you have this type of cosine sine shapes that you have here. So this is the lowest, oscillation that you can have on the structure that exists inside of it. And you can also see in these cases that the field here would also have, an X and Y direction. But Y here, it's independent of that coordinate. So it doesn't depend on one of the coordinates. The amplitude is only changing with the other coordinate. So here it will only change with respect to X. It doesn't change with respect to Y. So you get constant in one dimension and you get a smoother one in the other one. Let's then think back of your Fourier transform. If you take the Fourier transform in the smooth direction, you would have low side lobes. If you take the Fourier transform in the direction where you have a discontinuity, you would have higher side lobes. Think back 2, 4, 5 slides. I showed you the radiation pattern from the horn antenna. That's exactly what you saw. So that comes from this mode structure inside of this apertures in some ways, inside of these rectangle apertures. And of course, then we can compute those by these radiation vectors. So that means that we will start looking at horn antennas after the break, and we look at a few different types, or we do different tapering because we want to have different properties of them. And then we will start looking at the parabolic antennas and slot antennas and so on. But that we will continue with after the break. So, are there any questions?